Thanks, AJ, and thanks everyone for being here. Right, so like AJ said, I'm a PhD student at USC, and so this talk is about algorithmic social intervention. And really the motivation is the kinds of social problems that communities around the world have to deal with, so issues like disease, poverty, homelessness. And in response to these kinds of issues, governments and non-governmental organizations offer a variety of interventions, right? So they do services, outreach, education, trying to offer individuals additional opportunity or medical care, try to change their behavior for the better. And the fundamental problem in a lot of these situations is that we have limited resources. So we don't have enough sort of time or money to be able to deploy these interventions as widely as we'd like with everyone that we'd like to be able to benefit. And so the high-level question that motivates my research is how can we use artificial intelligence to improve this kind of socially impactful decision-making? In particular, then, the technical area that I focused a lot on is combinatorial optimization. And this is just optimization over a discrete set of actions. So I have an objective function that describes how good any prospective decision is, a constraint set that describes what the set of feasible decisions are for me to make, and then I'd like to find some decision from the set that maximizes my objective value. And this is quite a general framework, and there's lots of kinds of interventions that end up being modeled as problems like this. So I'm selecting basically who to get which sorts of resources. And so this just models the fact that since our resources are limited, the intervention is subject to constraints. The challenge is that while there's a lot of research about how to make decisions, how to solve optimization problems, when the problem is fully specified, we don't know nearly as much about making decisions under uncertainty. And by fully specified here, I mean that the objective function often depends on some set of parameters, right, that describe kind of the state of the world and the impact that your interventions will have. And the challenge is that a lot of the time we just don't know that, so we don't have enough information to evaluate the impact that our decisions will have on the world. And so the specific question that then motivates a lot of my research is how do we solve combinatorial optimization problems that depend on unknown parameters? And when we think about problems related to social intervention, there's unique challenges related to creating a unified approach that spans dealing with data and machine learning and so on, all the way to decision making and how we actually inform the interventions that we want to deploy in the field. And related to this, we need to be able to close the loop, right, from the lab to being able to deploy algorithms in the field, evaluate how well they do, translate those insights into improvements to the algorithms, and so on. Here's kind of a high-level snapshot of then the kind of specific topics that I've looked at to address these questions. And I've lined these up on an axis here, which is how much data that we have, because this is often what ends up kind of dictating the technical approach. And on the far left side is where we have relatively little data, so we don't have enough to formulate very good, precise models about the impacts of our actions. And so here I've worked on approaches related to robust optimization, so where you want to find decisions that perform well simultaneously across many possible scenarios. Then in the intermediate range is where we might not have a lot of data to start with, but we can gather more data. And this is costly. It's something that we need to do strategically. But if we can decide what the right data to acquire is, then we can use that to improve our decisions. Lastly, on the far right-hand side is where we have enough data to allow that to, in some sense, drive the decision-making. So we're going to train machine learning systems to work with a larger data set and use that to inform how we deploy an intervention. And so here I've worked on integrating together machine learning and optimization to sort of this kind of final goal of improving decision-making. And of course, all of this is in the context of wanting to be able to deploy algorithms in the field, right? The aim is, in the end, to have an impact in actual domains, to be able to see where algorithms work well, where they don't, and how that needs to drive improvement in the future. And so this last point is a really important piece of how I approach research. So I've been lucky to be able to work with lots of amazing experts in a variety of domains, primarily in public health, and work with them to be able to translate algorithms into practice. Here's the outline for the rest of the talk. I'm going to start out by introducing an application that sort of encapsulates a lot of these technical challenges. It's a good illustration of them, which is HIV prevention. And so we've applied similar ideas across a variety of public health domains, but this is one where that really sort of neatly illustrates the ideas and where we've been able to deploy the ideas in practice. So after introducing that application, I'm going to go through some of the kind of main technical ideas here behind robust optimization and how we decide how to gather more data before introducing then our field results from deploying some of these algorithms in collaboration with LA community organizations. And after that, I'll wrap up by introducing some more recent work on decision-focused learning and how we sort of integrate machine learning into the loop of all of this. Starting out then with the application. So the motivation for this project in particular is just the enormous issue related to homelessness that LA has. So this is a problem that is really close to home for us. At any given time, there's about 6,000 youth who don't have access to stable housing. And one of the key public health issues that this population has to deal with is HIV. So youth who are homeless have about 10 times the rate of HIV prevalence compared to youth who have access to stable housing. Accordingly, drop-in centers and shelters and other organizations that work with homeless youth will offer educational interventions to try to raise awareness about HIV and prevention strategies. But due to resource constraints, they can't deliver this intervention to all of the youth who might frequent a given center. Instead, they work with very small classes, maybe 4 to 6 youth at a given time. But to make up for that, they train these youth as peer leaders. So these youth are supposed to talk to their friends about HIV, who will hopefully talk to their friends, and so on, and you'll be able to amplify the reach of the intervention by leveraging the kind of latent social structure in the population. This raises a computational question, which is that given that I have only a limited budget for the number of peer leaders that I can train, who should I select in order to create the greatest overall influence spread? And this has been studied under the name of an influence maximization problem in the literature. The idea is that I'm given a graph as input that represents the social structure of the population, and I can select a limited number of seed nodes who will be initially informed. They can talk to their friends with some probability, who will talk to their friends with some probability, and this induces a stochastic diffusion process over the graph, where with some probability all of the different nodes are reached, and you'd like to maximize an expectation the number of people who get this information. Writing things down just slightly more formally, so given a graph as input, I'll have an objective function that describes the quality of the decision that I make. And this is a function of 2 parameters. The first is the set of people that I choose as peer leaders, which is the set S. And the second is a set of model parameters that describe how information spreads over the graph. And I'll show sort of a concrete picture of what that could look like in a sec. But given that I have access to that, then I can evaluate in expectation how many people will get reached by a given set of peer leaders, and I'd like to find a set that maximizes that objective value subject to a budget constraint that I can select at most k people. Here's the most common model in the literature for how information propagates over social networks, which is pretty simple. It's called the independent cascade model, and the idea is that each edge has a propagation probability, which just describes the likelihood that if one person receives information, that they'll communicate it to their friend, where all of these events are independent. And now the model parameters are just the collection of the propagation probabilities on all of the edges in the graph, and that sort of fully specifies the objective function. That's what you need to know to determine what the optimal decision is. I'm going to give just a brief amount of algorithmic background about how people typically approach these problems. And the key concept here is submodularity, which is, there's a formal definition on the slide, but it's really just the kind of intuitive phenomena of diminishing returns, that as you select more people as peer leaders, each additional peer leader only contributes less to the objective function. And this is because many of the people in the graph will already have been reached, so you don't need additional peer leaders as much. And when your objective function has this nice property, there's a very classical result that a simple greedy algorithm gets you pretty close to the optimum, and this works very well in practice. I'll also sort of just mention another approach here that's sort of been developed more recently, which is based on continuous relaxation. So the idea is that you start from this discrete problem where you either select someone as a peer leader or you don't. So you're taking these binary decisions, and you relax that into a continuous space. So you associate with each node a fractional decision variable that now describes the probability that you'll select that person as a peer leader. So it's a continuous quantity in the interval 0 to 1. And then your objective in this continuous space is the expected value of the set that you get when you choose people with those probabilities. And so you can show that by applying appropriate ideas from continuous optimization and then rounding afterwards, you can also recover this nice approximation guarantee. So I'm bringing this up because this will be sort of a set of techniques that we build on later in the talk. So there's a lot of ideas that have applied these kinds of techniques to influence maximization. But the assumption that's made almost uniformly across the board is that you know the underlying model exactly. So someone actually tells you what's the structure of the graph, what are all the propagation probabilities on all of the edges. And of course, this is really never the case in real life. And so I'm going to point out 2 particular forms of uncertainty. First is that we probably aren't going to know how influence propagates, in the sense that I'm not going to know what those propagation probabilities are. And this is particularly acute in a lot of public health situations. So for example, with homeless youth, there's very little data available about how information is going to spread. And but then even taking a step back, I don't even know to start with what the structure of the social network is, just who's friends with who, regardless of what those probabilities are. And it turns out that that's data that has to be gathered, and that's an expensive process. You end up having to actually go survey people face-to-face, ask them who they interact with. And so this is a huge bottleneck in being able to scale interventions like this in the field. So the main outcome of this project, then, is that we've worked together with partners in social work and community organizations in Los Angeles to develop algorithms that address these issues to be able to deploy interventions in a more scalable and effective manner. And together with these partners, we've worked to try out these algorithms in the field and measure their impact. So we've seen that this substantially improves the efficacy of the intervention, that we about double the number of people who receive HIV prevention intervention compared to the status quo. So now I'm going to go into a little bit more detail about the technical side of the work and how we get to that point. And I'll start out with robust optimization, where here we're looking at this first challenge that we don't know essentially the propagation probabilities, or in general, we don't have a good sort of ground truth model for the objective function. The idea in robust optimization is that instead of describing a single precise objective function, a single set of parameters, I'll just describe a set of parameters that are consistent with my prior knowledge about the world. So I'll have many different possible sets of propagation probabilities, each of which induces a different objective function. And then what I'd really like is a decision that performs well simultaneously across all of these scenarios, because then it doesn't really matter what the ground truth is. I'll do well regardless. And formally, that corresponds to a Maxmin problem, where I try to find a decision that works well even when the ground truth is selected by an adversary within this set of possible candidate models. This turns out to be really computationally challenging, though. So I showed you earlier that optimizing a single submodular function is a relatively easy problem. But when you try to optimize the minimum of submodular functions, it turns out that the problem is NP hard even to approximate. So you have to seek sort of suitable relaxations. And there's an additional challenge for influence maximization, which is that natural descriptions of the uncertainty set will be exponentially large. So you'll have to worry about exponentially many different scenarios. Here's a simple example where you have interval uncertainty on the propagation probability on each edge. So I just tell you that the probability could be between those upper and lower bounds. And now you can show that maybe I only have to worry about the upper and the lower end of each interval, but that still gives me two choices for what the probability could be on each edge. And if you multiply that out over the total number of edges, that means that the number of objective functions is scaling exponentially with the size of the graph. And so this is really problematic computationally, and it means that existing approaches that are sort of largely building on this kind of greedy algorithm are either heuristics or else they take exponential time to run for this problem because they have to actually enumerate all of the different objective functions. The main sort of theoretical contribution then in this piece of the work is the first polynomial time approximation algorithm for this kind of robust modular optimization problem, where the runtime is actually independent of the size of the uncertainty set, of the number of different objective functions. And instead, we have a significantly weaker requirement that you just have to be able to find the worst case function for any given decision. So you have to have an oracle that when I give it a set of peer leaders, it returns back to me, here's the worst case set of parameters for you, given that decision. And this can be computed much more efficiently. And so empirically, we observe that there's an order of magnitude speed up over the best previous heuristics for the problem. I'm not going to go into a ton of technical detail, but I'll sort of try to cover the main idea behind these algorithms. So the idea is that, like I mentioned earlier, we have to relax the problem somehow. And so the relaxation that we pursue here is to model the problem as a zero-sum game. So instead of taking a single discrete decision, i.e. what set of peer leaders I'm going to choose, now I'm going to choose a probability distribution over actions. And then essentially nature is playing on the other side of the zero-sum game to choose the objective function that's the worst possible for me. And so this means that we're optimizing over this continuous distribution over sets, not over choosing just a single set anymore. And this means that the guarantee that I get only holds an expectation, but it seems to be a good relaxation in practice. So the strategy then that we pursue is to look at the continuous relaxations of all of the different possible objective functions. So under each set of parameters, we can, that induces an objective function. We can take the continuous relaxation of that, like I sort of foreshadowed earlier. And then what I'd like to be able to do is to optimize the pointwise minimum of all of those functions in continuous space. And the main technical contribution here is to show that when we make this move from the discrete to the continuous domain, we can actually solve this, this Maxmin problem without having to deal directly with the underlying uncertainty set. So the move to the continuous domain allows us to reason only about the worst case function at any given point, and that in turn gives an exponential speed up for a large M. The high-level idea then behind the algorithm is to apply gradient-based techniques to this function, which is the minimum of the continuous objectives. And so the idea here is that you can get at least a super gradient of the function just by finding the minimizing objective at a given value. And I just need to differentiate that function. That gives me a gradient of my sort of composite objective here without needing to explicitly deal with all of the different objective functions. And so there's some technical issues that I'm glossing over here in ensuring that the optimization and the rounding procedure can work, but those are in the paper if you're interested particularly in those. But the main idea looks something like this. So I'll start out with my discrete set of decisions. So here a 0 means that I haven't chosen a node, and a 1 means that I have. And then instead of optimizing just over these discrete points, I'm going to optimize over their convex hull, essentially, right? So all continuous decisions that correspond to taking each of the nodes with some probability. My algorithm will maintain a feasible point within this set at each iteration. And then, given where it is, all of the different possible objective functions will have a gradient that's pointing in some direction, right? What you need to do to improve that objective. And instead of trying to reason about all of them explicitly, I'll just ask my oracle, what's the current sort of lowest value? Maybe the oracle tells me that that's F3. So then I'll just differentiate with respect to F3 here, and then find the discrete point that lies furthest in the direction of that gradient, and then take a little step in that direction. And I keep iterating this, and after some number of steps, you can show that this converges. And so the main theoretical result that we get is that this algorithm gives you that same constant factor approximation to the solution for the robust problem, but now we've actually removed the dependence in the runtime on the size of the uncertainty set. So I guess the takeaway from this portion of the talk is that while sort of creating nuanced models of influence spread is kind of computationally involved, we can give scalable algorithms by leveraging tools from the continuous domain. And what this buys us is that for a given graph, we have a sort of principled way of doing planning under uncertainty. But this has been ignoring the question of where that graph comes from in the first place. How do I actually know who's connected to who? And that's what I'm going to sort of switch to in the next part of the talk here. And this is something that, again, has been glossed over to a fair extent. So most algorithms for influence maximization will assume that someone just tells you the entire social structure of the population to begin with. That's just the input into the algorithm. But in reality, you don't know anything like that to start with. You start with nothing, and then you have to decide what data you need to acquire. And this is a really costly and time-consuming process. What we found working with social workers is that digital data sources are often inaccurate or missing entirely because of more limited access to technology among homeless populations. And so the data that we get from Facebook or something like that is essentially worthless. You have to go actually out into the field and ask people, face-to-face, who are you friends with? Who do you talk to at the agency on a regular basis? And this is really time-consuming. It requires about a week for the social workers that we collaborate with to go out and do this in the field, just for a set of 60 to 100 youth. And this is something that's not scalable remotely for a community organization to deploy on their own. They just don't have the resources to do this for one intervention. The question then is, do we really need this entire data set, right? Do we need to know the complete social structure of everyone in the population, or would it suffice just to get access to a smaller amount of data, like a subset of the population? And that would still enable us as long to locate influential nodes in the graph, as long as that data set is constructed appropriately. The idea looks something like this. You start out, AJ?
Just for clarification, Ryan. Actually here, you are not looking for people who know each other, right? You are looking for people who will share information with each other on a particular topic. Is that right?
Right.
So it is like, just to maybe give a little bit background on the particular application, what you're expecting is, the social worker is going to go and talk to me and say, tell this to your friends. But I may know Harsha and decide not to talk about HIV with Harsha, right? So there is this kind of the unknown thing, which is Harsha the person I would share this information with, kind of? Right. Is it also part of the problem?
Yeah. So the question is whether this kind of propensity to actually share information about HIV is something different than just being friends with people. And this is a really good point. So you shouldn't expect that people just talk to everyone about HIV. It's something that I think so far we don't have a great way of eliciting very trustworthy data about right now. So we can definitely find out just kind of who people at least come into contact with, and that's kind of the starting point. But then that additional step of wanting to share information is something that we don't have great data about, and that's why I think we still need to think about robust optimization and the sort of techniques to handle the additional uncertainty.
So basically, even if for the positive data points, for the links you observe, or somebody gives you like, I'm connected to this person, there's still the uncertainty whether they would talk about it with each
Right.
other.
Exactly. Right. But just in terms of, so unless anyone has additional questions here about this.
I think just to follow up on that, this is an analog because this is really not in the homeless setting, but you can imagine a setting where like a teacher may not be connected to all of his or her students, but could like maybe be more likely to share like some information of this nature, and so that also seems to be potentially something to consider. Maybe there's some analog of like just like more influential people like in a community that people tend to listen to even if they don't actually like know everyone.
In the realm of social domains such as HIV sampling, right, there are social science studied methods and channels of communication in which one chooses to distill information about this particular topic to others in the community, right? Did you guys try looking at those? Like, for example, if a teenager is trying to get tested for HIV, they might go to their local clinic under anonymity to talk to a local clinician who then diagnoses with the lab, who then, I don't know, are there like established channels of communication in particular applications that you've studied here for this example?
Right. Yeah. So I mean, so the question here was whether there are existing communication channels around HIV, and yeah, there definitely are. So the organizations that we're working with are already are offering access to free HIV testing. There's posters up about it and that sort of thing. And I think the challenge is that they just aren't getting like enough uptake on people actually entering that pipeline to begin with, right? So not enough people are starting to get tested for HIV. Like they're just not walking in the door to the clinic to start with and that sort of thing. So it's trying to raise awareness about this just like kind of in the background sort of the population. Yeah, and then sorry, so you were bringing up something about education here.
More like some people in the social network may have more influence over
Right.
regardless of like who they know.
Yeah. So other people are influential even if they're not like explicitly sort of friends with everyone in the population. Yeah. So this is something that basically gets at that like eliciting the right network data is really difficult because you don't just really want like who people like happen to talk to. You want like who they like will listen to about kind of sensitive health advice, and yeah, those two things aren't the same. I don't have a great answer. Like I don't know how to like elicit that information really well. So there's inevitably going to be a lot of uncertainty. I think the most we can get is kind of like, at least like who has the potential to have like interactions basically where that information could propagate.
This is a naive question, but if it's so expensive to get like information about the graph, like is it sometimes just better to, instead of collecting all this data, to just train more and more peer groups, right, and like spend your budget on like just finding more influencers, right, or just picking more people to educate?
Yeah, that's a great question. So there was a paper by Sudbury collaborators recently about this exact question, and so the answer is that to some extent it depends on the structure of the graph. So there are some graph structures where you can expect that just like seeding some more people at random will kind of make up for the difference in a carefully targeted strategy. We have not found that to be empirically the case in the graph structures that we've collected so far, at least. So we've seen in simulation experiments that there is, you get more utility. Like even if you give our method less seed nodes, right, it still does better than a random seeding strategy with a few more,
Gotcha.
So, but I think that's something empirically that people have to be thinking about. Okay. So then, unless there's additional questions, we'll.
I have a
Okay.
question about the earlier part, which is how do you overcome the oracle adversary assumption in practice?
Right. Yeah. So this depends on the exact sort of model for the uncertainty set that's used, and so. So for this sort of more interval uncertainty kind of idea, it's fairly difficult, but there are some techniques that are that work under a slightly restricted version of the model that you get, actually just a provable like optimization approach to be able to find the worst case set of parameters for a given decision. There's also uncertainty sets related to distributionally robust optimization, where the adversary is sort of perturbing the distribution over what edges will propagate influence and which won't, and there you can actually give really nice closed form or nearly closed form solutions to the adversary's oracle. But it depends very much how you've set up the problem, what the right algorithmic approach is there. Great. So okay. So then looking here at this network sampling problem, how you're going to elicit information about who's connected to who in the first place. And so here the process that we have in mind is that you'll survey someone just sort of at random from the population. You'll ask them who they're connected to. They'll reveal a set of edges. And then you can go talk to one of those people, right, and ask them the same question. That will reveal more of the graph. You can talk to someone uniformly at random again, and you'll continue iterating these steps until you're sort of satisfied with the picture of the graph that you've built up. And here we'll look at two different objectives. So first is the query cost. So how many nodes did I have to survey? And this is something that you'd like to grow pretty slowly with the total size of the graph. You don't want to have to survey nearly the entire population. And then you'll also look at influence spread. What's the expected number of nodes that you reach? And I'll measure this in comparison to opt, which is just the best that you could have done if you knew the entire network. And so this gives us an approximation ratio, which is how well does your algorithm do an expectation compared to what it could have gotten with full information. And we'd like this to be as close to 1 as possible. Unfortunately, in the worst case, there's really nothing that you can do. So there's a pretty easy hardness result that there at least exist families of graphs on which any algorithm that surveys a sublinear number of nodes has an approximation ratio that tends to 0. So you just can't have both of these two things at the same time. And the bad example looks something like this. You have almost everyone in the network is an isolated node, except for this little group of log n people who actually have some edges. And so to get any appreciable influence spread, you need to find this group over here. But because there's only log n of them, you have to survey pretty much the entire network to find them to begin with. So this is a really bad case for our algorithm, but of course it doesn't really look anything like real social networks either. And this prompts the question then of how can we use the kind of particular structure that's present in real-world networks to do better? And I've looked at two particular instantiations of this. The first is community structure, and the second is the friendship paradox. Starting out with community structure. So this is the intuition that real social networks tend to contain these kind of tightly knit subgroups that are then more loosely connected to the rest of the graph. And the intuition then is that information will propagate mostly locally within communities. And so a decent approximation to the true optimal strategy is to put one seed node in each of the largest K communities in the graph, if I have a budget of K seed nodes. And so we propose an algorithm that accomplishes this, at least sort of probabilistically. The idea is that you'll repeatedly sample a random node in the network, and then you'll explore the neighborhood around that node by simulating a random walk. So you'll just survey one of their neighbors uniformly at random, and then go to one of that person's neighbors uniformly at random, and so on. And this lets you get information about the local neighborhood around your starting point that lets you estimate the size of the community that that node is embedded in. So basically an estimate of how influential that node is. And then you can seed nodes that correspond to the largest K communities. So I'm sort of glossing over some technical issues here, but this is the main idea. And you can show that for graphs that have this particular kind of community structure, right? So if your graph is drawn from the stochastic block model, which is a common probabilistic model for communities, then this algorithm will get you a constant factor approximation to the optimal influence spread, but it only needs to use a polylogarithmic number of queries. And this is good, at least asymptotically, because it means that you have this really an exponential improvement over having to survey everyone, because now you only have to survey polylog people. But this turned out to be pretty difficult to actually translate into the field. So the algorithm that we proposed had these theoretical guarantees, but it was kind of brittle, because what happens when you go to actually deploy this in a homeless center is that you have to simulate these random walks, which means that I have to find a specific set of like 10 people in sequence, right? The algorithm says like survey this person, then survey this person, then survey this person, and half of those people just aren't even at the center that day, right? Or you can't find them, or who knows what. And so we needed to find sort of a more streamlined version of this algorithm that would still work. And the reason that we could simplify it is another structural property that we see in a lot of networks, which is the friendship paradox. And this is just the intuition that, on average, your friends are more popular than you are. So here's a degree distribution from one of the networks that we gathered. And on the left-hand side is the degree distribution for a random node. And so this is pretty skewed towards the left-hand side, right? So most nodes have pretty small degree. And then here we have the degree distribution of a random neighbor of a random node. And this has a lot more probability mass on higher degrees, right? So when you survey random neighbors, you tend to find higher degrees than if you survey just random people in the first step. And this is because nodes that have high degree are neighbors to many other nodes, right? So they're overrepresented when you sample neighbors. And this is pretty useful for designing algorithms because it means that this very simplified version of the earlier algorithm, we can expect to work relatively well. We'll just survey a random node and then survey one of its neighbors uniformly at random as well. And we'll iterate these steps a bunch of times. And the idea is that intuitively, this should balance between a couple of competing things I want out of my sampling scheme. It should give me sort of diversity in the first step because I'm surveying lots of different portions of the graph uniformly at random. But then the second step should bias the search towards more high degree or more central nodes that can give us more information about the graph and that are better candidates to be influencers. So now I'm going to briefly just show how we kind of combine these ideas together. So we need a single system that's going to work well in the field, that needs to minimize the need for special data and expertise and resources to be able to deploy it. And it also needs to handle the kind of domain-specific challenges just of working with homeless youth. So one thing, for example, that we ran into when we were deploying this was that the peer leaders that you invite to attend an intervention often just don't show up on the day of. And this is because there's a lot of things that could get in the way of a given youth from being able to attend, right? They could have been arrested. They could have not had enough money for a bus ticket. There's a lot of barriers that could prevent them from being able to attend. And your algorithm needs to be able to reason about these ways that things could actually go wrong in practice. So here's the final system that we put together that we call change. And so it integrates these three steps. The first is network sampling, which uses the mechanism that I described earlier to build up a sampled subgraph. Then it uses that information to feed into a robust optimization algorithm that reasons about parameter uncertainty, like I mentioned earlier. And then last is the actual loop that it selects peer leaders in. And in the practice, then, we make this an adaptive loop. So you select a small set of peer leaders. Remember, it's about 4 to 6 people in each class. You invite these people for the intervention, knowing that not all of them will show up, right? So you're solving kind of a stochastic optimization problem over who actually will end up attending. And then you observe who attended this class and use that information to drive the next round, basically to decide what areas of the graph you haven't covered yet, and so who you need to invite next for the next class. With that, then, I'm going to switch over to the results from when we've been able to pilot these algorithms in the field. And here we've worked. Question?
Is there a need for the kind of network sampling and the peer leader selection to be completely disjoint? Like, I'm thinking if you already got in touch with these people to survey them, like, does that influence their likelihood of becoming a peer leader? Or, like, you're already talking to them, right? So the likelihood of them not showing up, like, is there a reason that, like, when you're surveying someone, you can't also tell them to just not to tell their friends to not about HIV or something?
Right. Yeah. That's a good question. So whether why can't you just distribute the information like during the surveying process?
Take advantage of the fact that you've already talked to some people, right? Or
yes. Yeah. So the HIV prevention intervention that the social workers developed is actually like a full day or a half day sort of class, right? So it covers like a bunch of health information and then also like kind of how to communicate with your friends, how to be a peer leader.
Right. Gotcha.
Yeah. Right. So then, So this part of the talk is how we sort of try to deploy these interventions in practice. And so here we've worked with social workers at USC and with community organizations in Los Angeles. We've conducted a series of pilot studies so far, and the idea on each one is that we recruit a set of about 60 youth from a given drop-in center as kind of the baseline population for the study. We survey their social network, along with gathering sort of other baseline data, and then we use whichever algorithm to train about 10 to 12 peer leaders over the course of 3 different interventions, 3 classes. These peer leaders have 1 month to talk to their friends, spread information about HIV, and then after that 1 month, we call back all of the original 60 youth and survey them about who received information about HIV. And we do this for several different algorithms to be able to compare the impact of different seeding strategies on the final result. We've conducted 4 of these studies to date so far, each of which uses a different algorithm. We started out with the status quo approach, which is when agencies have kind of a strategic way of selecting peer leaders at all, they usually use degree centrality, i.e. just selecting the most popular people in the population, the nodes with the highest degree. And to that, we've compared a series of AI-based algorithms that we've developed. So Change is the most recent one that I mentioned here, along with 2 earlier algorithms that we developed, Healer and DOSUM. And the kind of salient difference that I'll point out here is that Change only surveys 20% of the nodes in the graph, whereas Healer and DOSUM are premised on having the entire social network as input. So they, in a sense, have to survey 100%. here's the first set of results. And here we're looking at information spread. What percentage of people who are not chosen as peer leaders nevertheless received information about HIV at that baseline, or at that 1 month follow-up study? And there's a couple conclusions here. The first is that the AI-based algorithms are doing much better than the status quo. So when we use degree centrality to select peer leaders, about 30% of nodes got information about HIV. And across all of the kind of algorithm-driven arms of the study here, we get about 70% of people who received information. And so we can significantly improve, at least in these early results, the efficacy of the intervention. And the second conclusion here, question?
Is it the same people who are administering each of the different algorithms?
So there's some, there's some personnel turnover over time, but it's the same, basically like social work team that's administering each of them, yes. And, right, yeah, so the same team more or less conducts each of these. And
how do you do this A/B study? Is because, the information propagates all the time, right? So if you kind of say, this week I'm using this algorithm, the following week I'm using this algorithm, there's still the effect of the first week probably on the second week in form of, how do you really measure?
Yeah, no, this is a good question, whether there's sort of like residual impacts from each intervention that build up in the population. And so the answer is that these are done both at different drop-in centers, right? These different agencies, which have largely disjoint populations. And so that's why we don't expect there to be sort of spillover effects between them. And then you can also exploit the fact that the population turns over, just sort of by nature. If you go back to a given agency in 6 months or 9 months, you expect the population to be almost entirely different.
So which ones, like what was the order in which these algorithms were conducted?
Let's see. So I think the order was healer and degree centrality. I don't know the exact order. It was those were 1 and 2, then DOSUM, then change. And yeah, so this is the results up through maybe last year or so. Okay. Right, so we see so we got that the algorithms do better, and that change also does as well as the other algorithms. And so that gives us at least an early indicator that you're not really losing anything by only subsampling the graph, which is good because it means that you can deploy the intervention a lot more scalably. So this is the first result, looking at information spread. But then we'd also like to know if that leads to concrete changes in behavior as a result of getting the information. And here's the second key result then, which is looking at essentially the conversion rate. So the percentage of youth who were not testing for HIV to start with, who got information and then started testing for HIV. And this is one of the key kind of behavioral indicators that the social workers are interested in. And we find that there is an appreciable conversion rate. So about 30 to 50% of youth who get this information start testing as a result of it. So no one actually converted in the degree centrality trial. This is probably because of a smaller denominator, that there's very few youth who got information to start with and are sort of eligible to convert then, would be my hypothesis. But we also find that then when we use change, we get about the same conversion rate, or maybe slightly higher. And so again, we're not really losing anything by using less information about the graph. Great.
It's kind of weird, but it speaks to the fact that the intervention doesn't work very well. Because you're only hitting just over 50% of the kids, and then only 50% of them actually get tested still.
Well,
sad.
Yeah, I don't think this is terrible in the sense, right? That
it's better than nothing.
Yeah, like there's a big difference between like anything that gives people information and then that actually like inspiring them to take action in their lives. Like there's some cost here that they have to like actually go to where they can get the test and so on.
There might be something that works better.
Yeah, no, I think it's very much like an open question on the social work side too, like what the best way to structure these interventions is. Great. So are there any other questions about the field results here? Okay. So with that, I'm going.
Sorry, everyone. How often did you actually get in touch with the original 60?
So at those 2 points in time, basically. So at enrollment and then at the 1 month follow-up.
I guess I thought you mentioned that a lot of times they won't be able to show up for like follow-ups or stuff like that. Like, did you have a lot of like sampling bias, I guess, in that? Oh, right. Okay. Yeah. So for the follow-up survey, so
I mean, there is flexibility, right? It's not just that they have to show up on one day. It's that people they're doing follow-up for about a week. People can take the follow-up survey online if they're not there, that sort of thing. And there's a monetary incentive, which helps, ensure that people come back and take it. So the follow-up rate isn't 100%, but it's maybe closer to 70%.
And just to clarify, it's actually like 240 people because it's 60 per group?
Right. So across all of the arms here, that's closer to 240 people total. Right, and this is still in process, right? So I was like just helping set up a new run of this a week ago. So we're continuing to do additional trials of change here in collaboration with these organizations.
From the organizational side, what kinds of, proof of concept do they need to structure their programs differently? So, for example, when you take change to the LA LGBTQ Center and you say, oh, these are results, are they like, great, now we're going to implement X, Y, and Z interventions as a result? Or are they kind of like, oh, get back to us when we have more testing results?
So I think in terms of what the decision makers of the agencies need, basically, to start implementing this. So the people that we've been working with are, have been very excited about it, and this is, potentially because they're the ones who are interested in research generally in the first place, right? That they're open to sort of trying new things. So I was just talking with the executive director at one of these agencies here again, about a week ago, and she's really excited about sort of thinking how we can apply this kind of peer-leader-based model across more of their programs. So not just in HIV, but around other issues like workforce development and job training and that sort of thing as well. So I think that at least my impression so far is that they're excited about the results.
I think one of the big challenges in this space is defining the objective function.
Mm-hmm.
Right now it is the number of people you can reach. But I can imagine that, for example, some people may be left alone because they are not part of the social network, and the algorithm never really chooses them because they have very little influence.
Right.
And it gets to all of these issues around fairness and what is the right metric. Is it okay for the algorithms to be focusing on these hubs and leaving other people on the side? So I think there's this whole longer discussion, and it's not your discussion, right? It is really the social workers need to really think about what is the right objective function to give to this algorithm, trading off those problems.
Yeah, these questions around fairness and representation are really important, and that's, it's something even we've been hearing more of in the CS community too, not just from the social workers. And so it's something that intuitively we think that the algorithm is probably better than the status quo, right? Because the status quo was select the popular kids, and that's really just a little clique of people. And here, at least, what you tend to get out of the algorithmic solutions is more that it's trying to pick people from all of the different kind of subcommunities of the network, which is an improvement, right, in terms of fairness or that sort of consideration. But it's not something that was an explicit design goal for the algorithm, right? That's sort of a fortunate thing that happened, and so now we're looking at more how do you sort of what's the right way to explicitly model these sorts of concerns.
It would be great for you to visualize the network structure and who gets reached by these algorithms, and have that visualization just for discussion.
Yeah, I think hopefully in another few months or something, we'll have some stuff to show around that. It's definitely something we're thinking about. Great. So, anything else about this field part of the work? Okay. So now I just want to sort of touch a little bit more quickly on a more recent project, which is around integrating machine learning and optimization in these kinds of interventions. And the focus of the talk so far has really been sort of coping with limited data. And so now I'm going to talk a little bit about situations where we do have some data, and we want to think about how we can use machine learning to support decision making. So an example of how this might happen in the HIV domain is that a lot of the time we have administrative data that's probably kind of correlated with the social network. So you have things like the times that people checked into the shelter or who attended programs together. And this isn't really the ground truth social network, but you expect that maybe people who are friends tend to come into the shelter at the same time or something like that. And so there's latent signal here that you could exploit in order to improve your knowledge of the underlying graph. And this is then just sort of an instantiation of a problem that crops up across many domains, which is a sort of combination of learning and optimization. The idea is that you'll have data that you can observe. You'll use that to build a predictive model that infers something about these parameters that you don't know. you'll take your predictions and feed them into an optimization algorithm that then outputs whatever the correct decision is for those parameter settings. And the way that we typically approach these problems is in 2 stages. So we start by training our machine learning model, where the goal is to maximize predictive accuracy according to whatever loss function you choose. Then you take the results of that, and you plug it into your optimization algorithm, which has the goal of maximizing the quality of the decision that's made. The challenge is that, in general, those 2 objectives aren't really the same thing. And so maximizing accuracy is not the same thing as maximizing just the quality of the decision that you get at the end of the process. So the saying here is that all models are wrong, but some are useful. And this is particularly acute in sort of complex or noisy low-signal learning domains, where no model is going to be making perfect predictions. And so your loss function is basically telling the model what errors are OK and which are not, right? Where should it prioritize being accurate? And the 2-stage method of training here then isn't really aligning the process of training with the end goal of what we actually care about out of the final system. So here's what 2-stage training might look like in this domain, right? I start with a set of features for the nodes. I crank those through some sort of predictive model. I get a prediction for what the graph looks like. And then on my training data, I compare that to what the ground truth graph actually is. And then I update my model parameters to bring those 2 closer together, right? I just have some loss function like mean squared error or some classification loss that measures how different these 2 predictions are. But what I'd really like to do is take that prediction, feed it through my optimization algorithm, get the set of peer leaders that it recommends, and then update my predictive model such that those peer leaders are better with respect to the actual ground truth graph, so that the quality of the decision that is made as a result of the optimization algorithm is improved. So really, I'd like to train this entire process end to end here, instead of just stopping at the quality of the predictions. The approach then that we propose here is to train the entire system end-to-end with gradient descent, which essentially requires that you have to be able to differentiate the solution to your optimization problem with respect to your model parameters. So you have to say, how do my predictions influence the decisions that the optimization algorithm recommends? And if you can do that, then you can just train the entire thing with gradient descent. And so this is an approach that's been explored recently for convex optimization problems. And the challenge then is that in most of these situations, we're making discrete decisions. And this is problematic because derivatives through the optimization algorithm don't actually exist, right? It's just a discrete quantity. The solution then that we pursue is to use continuous relaxations. So we take the discrete combinatorial problem, we use an appropriate continuous relaxation of it, we differentiate with respect to that relaxation, use that for training, and then at test time we can round to get discrete decisions. And so for this particular subclass of submodular problems, it's using the same continuous extension that I showed you earlier, where instead of optimizing over the 0 or 1 decisions of who you choose, you optimize over the continuous variables of the probability that you choose them. So then the main thing that you need to make this approach work is how do you actually compute these derivatives of your optimal decisions with respect to the parameters that are predicted. And the idea here is that once we've moved to the continuous domain, any locally optimal solution has to satisfy the KKT conditions. And so that gives you basically a set of linear equations that have to hold around an optimal point. And so you can differentiate those equations at the optimum, and that will tell you how your decisions change with respect to your predictions. So the kind of technical piece of the work is to provide appropriate relaxations, iron out some issues, prove that this works for a couple common subclasses of discrete problems. So we look at problems that can be modeled by linear programming, which includes a lot of classical things like bipartite matching or shortest paths and so on. And we also look at submodular maximization problems, which includes influence maximization along with a host of other examples. We can do experiments then in a set of domains that we have data for using both real and synthetic data. And we're comparing here the quality of the decisions that we get out of both training methods versus the just ground truth predictive accuracy, and seeing how these 2 different objectives for training differ. What we find is that in terms of just solution quality, right, the final decision that you get, this decision-focused learning improves optimization, in some cases significantly. So it's in the range of 15 to 70% in the domains that we looked at. But the predictions are less accurate overall compared looking at kind of standard loss functions. And here I'm going to show just one example, kind of visualizing what this looks like. And this is a simulated network intervention task where I'm trying to predict the probability that each of a set of different outreach channels is going to reach all of the different nodes in the population. So here's the ground truth matrix, where a dark entry means that there's a high value for that probability, right? So that entry in the matrix is bigger. So the ground truth is pretty sparse, but it has an appreciable number of entries here. And the two-stage prediction basically just picks up on sparsity. So it realizes that like most of the entries are 0 here, and so it predicts something that's very sparse. Most of the entries are 0. That looks pretty good with respect to essentially any standard loss function, right? Like mean squared error, cross entropy, or whatever. This is a pretty good prediction with respect to the ground truth. But it's not actually very useful, right? It doesn't tell us relatively who's a better peer leader and who isn't. By contrast, the prediction that we get out of our method here on the bottom looks absolutely nothing like the ground truth, right? It gives us this really weird like barcode shape here, which is just visually like nothing like what the ground truth actually is. So it's failed to recover the truth in some sense. But this turns out to actually give us much, much better decisions when you feed this through the optimization algorithm. And an intuitive reason for this is that it picks up much better on actually the relative differences between potential outreach channels that influence which ones you should select for your optimization problem. So here, if we sort of roughly score different channels by their weight, like basically the sum of their row of the matrix, which is just kind of an aggregate coarse measure of how influential they are, we find that with our method, its predictions for these outweights are very well correlated with the ground truth. Particularly at identifying these outliers that have high weight, even though the magnitude is totally off, right? So it predicts that all of the channels have weight at least 13, whereas there's lots of them that are actually clustered around 0 in truth. When we train for accuracy with this kind of two-stage approach, it's much better at identifying that the bulk of things are close to this 0, 0 point here, right? So most channels are not influential. But it's much sort of weaker in terms of the correlation, especially out in the tail where you actually need to identify the outliers that are useful for the optimization problem. And so this gives us sort of an intuitive understanding of how the model is learning to focus on qualities that are relevant for the optimization problem at hand. OK, so then just to wrap things up, so the kind of overall focus of the talk here is that really important social issues behind the scenes present opportunities to use optimization and learning to improve decision making. So we've looked at interventions for disease prevention, homelessness, these sorts of issues, and how computational techniques can improve decision making. But that finding algorithms that can actually be deployed presents a lot of new research challenges. We have to think about uncertainty, how we integrate data and decisions together. But then when these pieces come together, that this can be a really powerful thing, that we can really improve the lives of our fellow humans. So, thanks.